Okay, the graph below shows a 120-second section of Yestin's car journey to work this morning, right? So his speed there, meters per second, over 120-minute section, a 2-minute section. So then it says, at t equals 50 seconds, estimate the acceleration of Yestin's car in meters per second squared. Leave your answer as a fraction. So remember, speed is given as meters per second, yes? You could write that like that, couldn't you? Meters per second, meters over second. But whereas acceleration is meters per second squared. So that's important there to recognise that. And to get then 50 seconds, well, on your graph, you need to go to 50 seconds, which is here, and pinpoint that on the actual graph here, the curve, okay, at 50 seconds, so we're there. And we're then going to draw tangents, right? That's how you get the acceleration or speed time graph. And the clue, of course, as well, it says estimate, right? So tangent is going to be an estimate because it's hard to get this drawn perfectly. Some people will draw it differently to others. But when you draw a tangent, just make sure that it does touch the curve there at one particular point, right? That's what the tangent is. It touches it at one point, and it's also got to go in that direction. So it's no good if it's going in a completely different direction, right? And you can't cut the curve. It's got to touch it. So we get it in the same sort of direction as the curve is going there. Okay. So there's my tangent. All right. And it touches there. That will do. And what you do then with the tangent is you've got to pick two nice points, right? And it's not that easy on here, right, to pick two nice points. But we need to pick points that will work for us, so that we can work out then what the gradient is. Okay, and the gradient is that gives you the acceleration. So two nice points. Perhaps we can pick this point here. That's quite nice. I think it goes through nice values there. And maybe we can pick, we can choose, what should we go for? Maybe we'll just go to the axes there. Okay, so we draw a triangle. Okay, so we're going to go across. Then we go up. So we need to work out now what this rise is. Okay, so it's going from 20.5. Well, the scale isn't very nice, isn't it? It's 20.5 there. That's what the scale is. And this value here is 32.5. Okay, so this will be 32.5. I'll write it down here, otherwise I can get messy there. 32.5. Take away 20.5. If you work that out, you get 12. Okay, so the rise is 12. Okay, 32.5 there, take away 20.5, which is 12. And then the step is going from here, which is 0, that's nice, all the way to 70. Okay, so it'll be 70, take away, use my scale, 70, take away 0. So I get 70. So the gradient then, or the acceleration, is the rise divided by the step. Okay, so that will be 12 divided by 70. Okay, so it says leave your answer as a fraction. We should really simplify it, I suppose. It doesn't say though, but you know, we could halve top and bottom here, 6 over 35, and that's it, right? That's pretty much what I've got. Can't go any further with that. You might have something different. Okay, yours might be different, but if you change this to a decimal, it'd probably be similar to what yours is as a decimal. Okay, even though it might be slightly different to mine because your tangent might be different. So you've got an idea if it's right by comparing the decimals. Okay, part 2 says at another time, Yestin calculated the acceleration to be 0.24, okay, meters per second squared, and 0.24 recurring, right? Write this recurring decimal as a fraction. So remember, to write recurring decimals as a fraction, we sort of say let x equals 0.24, and then what's recurring is the 4, okay, so there's loads of these. 10x then, remember we do this method times it by 10, so you get 2.4444, and so on. Then, you know, you check after the decimal point to see if there's consistency there, and it isn't because they're different. So we're going to times it by 100 now. 100x, and if you times x by 100, it moves 2 places. So you get 24.444. Okay? And then, you can see after the decimal point, they're identical. These two are identical. after the decimal point. So we can take away 100x, take away 10x is 90x. And then 24 take away 2 is 22. And then the 0.4 take away the 0.4 is 0. So you get then x equals 22 divided by 90. Okay? And you can leave your answer like that. Usually these questions, you know, they never ask to simplify, and they're not asking to simplify. If you wanted to, you could halve top and bottom, you get 11 over 45. Both will get you the marks there, right? Okay, part B then, it says, calculate an estimate of the distance travelled by Yestin's car in the first 80 seconds of his journey. You must consider the speed of the car when t equals 0, 20, 40, 60, 80. Now, when they say this, right, they're giving you ordinates, and you've got to think about the trapezium rule, okay? Because remember the trapezium rule, they give you ordinates. They say, look, these values here you've got to consider. They haven't mentioned trapezium rule here, but they mentioned distance. And with a velocity time graph or a speed time graph, the area under the curve gives you the distance. Okay, so between 0 and 80. So what I'm going to do is I'm going to draw trapeziums. Okay, I'm going to draw trapeziums here. So at these intervals here, 40. Okay, let's get this right. 60 and 80. I'm glad I didn't write on my graph now as I started to there, because it's going to get quite messy if loads of numbers on here. Now, the trapeziums, of course, are formed by joining up the ordinates based on the ordinate values with these strips here. Okay, so then you could see if I turned it on its side, I'd get trapeziums. Okay, so if you look down its side, you've got yourself trapeziums where these sort of sides here are parallel, aren't they? That makes sense. So loads of trapeziums. So it says up to 80 seconds, doesn't it, in the question? So if I call this region 1, region 2, region 3, region 4, right? So then what I can do is work out the area of each region, and that will give me the distance then for each region. So area 1, so of course then remember, you know, the trapezium formula, okay? It's on page 2, so you don't need to remember it. So it's half a plus b. Now a and b are the parallel sides. So a there is 10 and b there is 15, right? That side there is 10 and then the b side then 15. So 10 plus 15 times then the distance between them. And the distance between them, is the height, yeah, is 20. That's the distance between them, 20. So you've got this. Okay, so let's take our time on this. Half times 25 times 20. You'll multiply them. Now, what's good about multiplying, doesn't matter what order you do it in. So work that out. Got to work that out first, of course, to get 25. But now when I multiply them, it doesn't matter. You could do half times 20. Okay, so multiply these first. Half times 20 is 10 times 25 is 250. Okay, so it doesn't matter the order. You could do half times 20 times 25. Area 2. Okay, half. What have we got? 15 here and 25 there. Times the height between them, which is 20. So that'll be half times 40 times 20. So half times 40 is 20 times 20 is 400. Area 3. Half 3, that will be 25 there, and that will be 30 times the height between them. So it'll be half times 55 times 20. So again, half times 20 is 10, times 55 is 550. And area 4, half, so there we've got 30 and 30 at the end. That's quite nice. 30 plus 30 times 20. So then that would be half times 60 times 20, and half of 60 is 30 times 20 is 600. So all you've got to do then is add them up to get the total, and we add them up, add the zeros there, add the tens, so it adds up to 10, so 0 carry 1, and then add the hundreds. 2 and 4 is 6, add 5 is 11, add 6 is 17, add 1 is 18. So 1800 is what we've got there. So 1800 meters. All right. It says in part 2, hence calculate an estimate for the average speed of Yestin's car for his entire 120 seconds. So remember, average speed is total distance divided by time. Okay, now the total distance in this case, well, we've got 1800 meters already, haven't we? Let's think about what the distance is here with this. Okay, now because it says the whole 120 seconds, isn't it? So we need the area here. But if we think about the area here, it's just a rectangle, isn't it? This is just pretty much a rectangle. We don't need to do trapezium for this section here. This is a rectangle. It's a rectangle. The length of it is 30. The width of it is 40. So this will be 30 times 40 in total. Okay, as a sort of complete rectangle. Okay, 40 this way, going across here on this scale from 80 to 120 is 40, 30 up there. So 30 times 40 will be 1200, of course, because 3 times 4 is 12, and add the 2 zeros. All over the total time of 120. So then that would be 3000 divided by 120. And then these will cancel. Okay, so you've got 300 divided by 12. And of course 300 divided by 12 is 25 meters per second.